All right, we have just learned that a definite integral is a way of looking at a limit of Riemann sums, which we can use to calculate the area under a curve, or we can use to calculate position given velocity. And now we're going to start evaluating integrals. And there are different ways of doing this. We're going to start using sums and limits. And I'm going to be honest, it's going to be pretty nasty. The calculations are not very nice. But what's going to happen is, moving forward, we're going to learn different rules of integration, similarly to how we learned different rules of differentiation, like the power rule, the product rule, the quotient rule, the chain rule, etc. And these rules are going to make things a lot nicer to solve than actually dealing with the limits of sums. It's kind of like the limit definition of a derivative, right? You could use that to differentiate any function, but you have to be a little bit smart about the different tricks that you're using to evaluate those limits. And in the end, it's just a lot easier to use things like the power rule, the product rule, the chain rule, etc. And we're going to see something similar when we're dealing with integrals. So first of all, I'm going to give you a few formulas that are helpful for calculating integrals using limits and sums. All right. These are some formulas that tell us how to add up different sums, the sum of I from 1 to n, the sum of I squared, and the sum of I cubed. And we're going to be using some of these in the calculations that we're going to do for our very first definite integral. So let's get into this. I'm going to write it right here, just to use as much, to give us as much space as we can. Evaluate the definite integral from 0 to 3 of x cubed minus 6x dx. Okay. So because we are integrating from 0 to 3, that means that the interval that we would be looking at goes from 0 to 3. And we're eventually going to need delta x. And we know that delta x is b minus a over n. In this case, that's going to be 3 minus 0 over n, which is just 3 over n. And then we knew that x sub I was a plus I delta x. Of course, a is 0, right? The left endpoint or the lower limit is 0. So that term is going to go away, and we're just going to have I times delta x. So it's going to be 3I over n. Basically multiplying 3 over n times I. I think that's the nicest way to write that. So let's see what we've got here. This integral, which I'm going to write again over here, the integral from 0 to 3 of x cubed minus 6x dx. This is just a way of writing the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I delta x. And we actually have ways to represent x sub I and delta x. We've got all of that in terms of I and n, so we can write that out. We've got the limit as n approaches infinity of the sum as I ranges from 1 to n of... Now we have to look at our function and evaluate it at x sub I. The function is x cubed minus 6x. And this is our expression for x sub I, 3I over n. So this is going to end up being, I'm going to put it in brackets just so that everything looks nice. We've got x cubed, x sub I cubed, so that's going to be 3I over n, quantity cubed, minus 6 times x sub I, so it'll be 6 times 3I over n. And then our delta x we saw was 3 over n up here. So I'm just plugging in for delta x, x sub I, and our function. And then we have something that's only in terms of I and n. And so theoretically, we should be able to take this sum, and then once we've done that, take the limit as n approaches infinity. Now, let's simplify what's going on inside the brackets. I think that'll make our life a little easier. So we've got the limit as n approaches infinity of the sum as I ranges from 1 to n of... Now, when we cube that, we get 27i cubed over n cubed, and then minus 18i over n. And that whole thing is going to get multiplied by 3 over n. So we should distribute that 3 over n inside there. That's a good next step. So we still have the limit of the sum. None of that has changed. And then when we distribute the 3 over n, that's going to give us an 81i cubed over n to the 4th minus 18 times 3 is 54i over n squared. Good. And what I'm going to do next, we've got this limit of this sum, and there's these two different terms that we're taking the sum of. I'm actually going to split it up. So I'm going to take the sum of this minus the sum of that, just so that we can look at each of those individually. So we still have the limit as n approaches infinity. I'm going to use squiggly braces here just so we can put kind of everything on the inside. And then that's going to be the limit of this difference of two sums from 1 to n of 81i cubed over n to the 4th minus the sum as I goes from 1 to n of 54i over n squared. Now, the reason I'm splitting this up is just so we can look at each of these two terms kind of separately within respect to the sums. When we're looking at this sum, the variable that we're working with is actually I. The thing that's changing in each term of this sum, because remember, when we've got a sigma notation, that means we're adding the same thing over and over again, and what changes each time is I. In the first term, I is 1, in the next term, I is 2, and then 3, all the way up to n. But in each of those terms, the 81 and the n to the 4th are the same, and so they're effectively a constant that's getting multiplied by I cubed. 81 over n to the 4th, with respect to I as a variable, is a constant, and so we can actually pull those outside of the sum, and the same thing over here with 54 over n squared. Let me show you what that looks like. We've got the limit as n approaches infinity of, I'm going to write this 81 over n to the 4th times the sum as I goes from 1 to n of I cubed, and then minus 54 over n squared times the sum as I ranges from 1 to n of I. All right. I imagine this step might be a little scary for some of you. I'm going to try and explain it once more. When we have a sum based off of sigma notation, we are adding together a whole bunch of terms. And the only thing that changes between those terms is the value of I. In the first term, I is 1. In the next term, I is 2. In the next term, I is 3, etc. All of those terms are going to contain an 81 over n to the 4th. So it's almost like we are factoring that out and bringing it outside the sum. So we only have to actually do the 1 cubed plus 2 cubed plus 3 cubed, etc. If that makes sense. The 81 and the n to the 4th can effectively be thought of as constants if we're considering I as our variable, which is exactly what we're doing in these sums. So now once we've done this, notice that we have the sum from 1 to n of I cubed, and we have a formula for that up here. That is something that I'm just handing you on a silver platter. I'm not going to show you where that formula comes from. You can Google it if you want to. But that is a formula that tells us what that sum is. We also have a formula for the sum of I, as I goes from 1 to n. That is up here, so we can go through and plug those in. So we've got still the limit as n approaches infinity of, but then we're going to have 81 over n to the fourth times n plus 1 over 2 squared. That is the value of this sum. And then we have minus 54 over n squared times the other sum, which is n times n plus 1 over 2. Now, there is some simplifying that we can do in each of these. We can cancel out 2 of the n's in n to the fourth with 2 of the n's here, because remember this is n squared. And then the same thing over here. We can cancel out 1 of the n's down here with 1 of the n's up there. We can also cancel out a 2 in that 54. So I'm going to bring everything up here and do some of that cancellation. When we cancel 2 of the n's on the left-hand side, we're going to have 81 over 4. If we look at the constants, right, we've got the 81 and 2 squared is 4. 2 of these n's canceled out. So we've got n squared left. And then this n squared canceled. Like, that was the 2 n's that canceled. And then we still have n plus 1 squared. Perfect. And then in this second group, 54 divided by 2 is 27. And then we can have 1 of these n's cancel out. And then we've got times n plus 1 over n. All right, we're getting there. I promise we're getting there. Okay, I'm going to rewrite the limit. And in the next step, what I'm going to do is I'm going to take this fraction, n plus 1 over n, and we can rewrite that as 1 plus 1 over n. If we were to actually divide the two terms separately, we would get 1 plus 1 over n. And we're going to get the same thing here, except since they're both squared, it's going to be squared. So we're going to have 81 over 4 times 1 plus 1 over n squared minus 27 times 1 plus 1 over n. And notice we're taking the limit as n approaches infinity. What happens to 1 over n as n approaches infinity? This gets closer and closer to 0. So the limit of that term is 0. 1 plus 0 is 1, and 1 squared is 1. So this whole thing becomes 1, and that whole thing becomes 1. And by direct substitution, we've got 81 over 4 times 1 minus 27 times 1. And if you go through and get a common denominator and combine those, you end up with negative 27 over 4, which is equal to negative 6.75. And that is the value of our first definite integral. Now, you're probably wondering why we got a negative answer. Among other things, this is a mess of a calculation. It is so many steps with limits and sums, and we're relying on formulas that you don't even know where they came from. This is a mess, and you probably feel like I did not do a good job of teaching you what this is. And in essence, that's kind of the point. This is such a mess that this is not how we're going to evaluate integrals moving forward. If we had to do this for every single integral we wanted to integrate, it would be an absolute mess. So I'm showing you how absolutely rough it is to try and calculate one of these by hand with the limits of the sums and everything, so that you can appreciate the rules that we're going to learn later to make things easier. And I'm not going to spend an hour going through this example super slowly so you understand every single point, because that's not the point of this. The point of this is for you to see one example, maybe two examples, if you look at another video later, of how we do all of this if we're actually doing the limit of the sum explicitly. And then we're going to see some theorems and some strategies that make this all simpler. But very quickly before we finish, why did we end up with a negative answer? We know that an integral is the same as a limit of a Riemann sum, and we saw that those give us areas under rectangles. Well, if you look at the graph of this function, x cubed minus 6x between 0 and 3, boom, you can see that there's a part of this graph that lies above the xy axis, but then there's also a part that lies below it. And when we're thinking about the area underneath a curve, and we're doing Riemann sums for approximations and then the limit to get the exact answer, and we're dealing with integrals to calculate all of that, any area that's above the x-axis is contributing positively towards that integral, and anything that's below the x-axis is going to end up being a negative contribution to that. So this whole integral that we calculated of x cubed minus 6x dx is actually equal to the positive area, the area that's above the x-axis, minus the area of the region that's below the x-axis. So all of the examples we looked at earlier had our graphs above the x-axis. So all the area we were contributing or calculating was positive. But in this case, we've got the graph dipping below the x-axis, and so we count that portion as negative area. I know this is a lot to take in at once, but I promise it will be okay.